Okay, Rishikesh Ijakul Rahman. Am I pronouncing your name correct? Ijakul Rahman and Rishikesh. Unmute yourself. Rishikesh, I don't think others will join because it's already 15 minutes are over. And Ijakul, you also unmute yourself. I think he also left. Ijakul, unmute yourself. Yeah, it's okay. Okay, no problem. Okay, no problem. So, okay, no problem. So, just both of you let me know, like one by one, like which course you are studying, like what you are studying, and why did you take this course? Like, are you a BTech student or MTech student? Which degree students you are? So, and after that, you tell me why did you take this course? Rakesh Verma, at least one person has joined. Okay, Rakesh Verma, unmute yourself. Rishikesh and Ijakul, am I pronouncing your name correct? Ijakul. Ijajul. Yeah, Ijajul Rahman. Okay. Ijajul. Now you tell me, like, are you a BTech student or MTech student, and why did you take this fundamental combustion course? Okay, 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 okay. Okay, fine, I understand. So basically, this course credit will be included in your coursework, right? Uh, Ija- and see, for the PhD, you need to complete like certain courses. You need to complete minimum at least 4 courses you are supposed to complete. So will they consider this course in that? Okay, so basically, at least you will pay attention, like because this credit will be added to your coursework. Okay, okay, and what about Rishikesh? Yeah. Okay. I understand. I understand. Rishikesh. Now you tell me, like, why did you take this course and like, which are you a BTech student or MTech or which course you are studying? Okay, Okay. Okay. What about Rakesh Verma? Rakesh Verma, can you introduce yourself? Just let me. Yeah, yeah, you are audible. Okay. 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 So no one is like no one is undergraduate level here. I think all have completed their graduation. Okay, so myself Amit Yadav, and I am third year PhD student in mechanical department. I am also working in thermal stream. So basically, I am teaching here. Basically, I need to complete my TA work, and actually, I am a PMRF scholar. So like PMRF have certain TA duties, so that will add add to my TA work. So I am supposed to complete approx 50 hour of TA work in every year. So with this, if I teach 2 hour every week, then it will complete my TA work. Because of to complete my TA work, I am working here. Okay, so this is just like this is first class. So this is just an intro class. So you like I hope you have solved the that week one question. All of you have solved. Uh, yeah. And yeah, you must have that watched that week one videos. They are like week one videos have already uploaded. Okay, so if you have doubt in week one video, not in week two, only in week one video, then you can discuss those doubts. And after, like after that, we will start solving the question. We will solve some question after that, but before that, you can ask your doubts. If you have some doubt, otherwise I will start solving the question. Anyone want to ask some doubt in week one syllabus? Week one. You can share your screen, or it's up to you. You can share your screen. Some specific doubt you have, you can ask. It may be a very fundamental doubt. See, it is like week one is very easy. So from next week we will be having like what I can say, like core combustion subject will start from next week only. It is just a fundamental of thermodynamics that week one. Okay, so like I will give you some question, and you solve that question, and you in the chat there is like there is an option like some like where you can send the message. So as soon as you get the answer, you send the message. Three of you. The question will be very easy, and those questions are similar to the assignment question that you are getting. Okay, it's fine. Uh, yeah. Okay, I'm sharing my screen. I will share the question. Shiva Kumar Reddy, unmute yourself. Yeah. So guys, can you see the question? Can you see the question? Hello, am I audible? Yeah, yeah. Can you see the question? See, this week actually, from next week onward, I will be solving the question. But this week, like I have already solved the question, so like I will discuss the solution. First, you try to solve, and after that, we will discuss the solution. The thing is, right now I don't have my tablet with me, so I can't solve the question. So I will discuss the solution with you. But from the next week onward, I will be solving question in front of you. So I will give you the question. Now you try to solve that question. Or see, one more thing. Or do you want any other thing that I can help you? Like, do you want me to explain the PPT something? Is it so? Or do you want to solve the question? Like, I'm trying to take your opinion. What is best for you? I will do that. If you want me to explain the theory, that is also okay for me. If you want me to problem solving session, that is also okay for me. So I want to take your opinion. Guys, please speak. What is better for you? Yeah. What about other? Psychometry. See, psychometry will come, and I don't think it is in the that fundamental combustion. I don't think it is in the fundamental combustion. So problem related to fundamental combustion, that is fine. See, if you want specific, then I can explain the psychometry. It's easy only. Maybe next week I can discuss some question psychometry, but that is not related to fundamental combustion. Yeah. Okay. 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 So you can ask that question. Can you share that question? Can you share that question? Can you share your screen and you share the question? Okay. 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 This thing is noted. Definitely I will explain psychometry. Yeah. For about what about others? Shiva Kumar Reddy. What is your opinion? What do you want? Do you want questions or do you want me to explain the first explain the theory and then solve the question? Shiva Kumar Reddy, can you speak? Shiva Kumar Reddy, unmute yourself. I don't think he is there. Okay, okay. Okay, so question number one is there in front of you. Can you answer that question? Question number one. It's a very easy question. Guys, can you answer the question number one? What is the answer of question number one? Yeah. What about others? Are you agree or not? Other than Rishikesh, Ijazul and Rakesh, you also reply. If you don't want to speak, then at least write in the that message box. Okay, okay. Ijazul, I think you are there. I hope you are there. Hello, yeah. Ijazul, are you agree that answer is zero or not? Might be zero. Why might be zero? What can be the other answer? Okay, who is this? Yeah. Ijazul, what you were saying? What can be the other answer? Why you are saying like it might be zero? Uh, See, question is there in front of you. Are you able to read the question? No. Are you able to read the question or not? Is this? Are you able to read? Yeah, Ijazul. Okay. So, are you able to read the question? Is this visible to you? Arak, please keep it. Okay. No. The thing is, I need to see like what you guys are replying. So that is why I'm not keeping it full screen. But see, I will try 125. Now, is this visible? No. Okay, I will zoom it more. Yeah, question is visible to you. Okay, Izadul, it's a very easy question. Izadul, it's a very easy question. Basically, it is asking the change in the internal energy. So internal energy is the state function. So if it is like it is moving from state 1 to state 2, and then again it is coming from state 2 to state 1. So there is like the net change, like what I can say is see, the in the entire path, it is in the state 1 only. So it is a state function. So the change in the internal energy is zero. Izajul, are you agree? Yeah. Yeah. So because see, you think in that way, whatever is the state function, if the state is same, then that property state function, that property will not change. So that internal energy depend on the state. It does not depend on the path. So like heat and work is a path function, but internal energy, enthalpy, entropy, these are the state functions. So it is asking the change in the internal energy. So it is a state function. Since it is like it is moving from state 1 to 2, then again it is coming back to state 1. So change in the internal energy is zero because it is a state function. Okay. So we will come to the question number 2. Can you answer the question number 2? Okay. Okay. Yeah, take pen and paper and solve the question number 2. And now, if you get the answer, then you reply. I will wait for 5 minutes, and after that, I will explain. Total pressure is 1.5 bar. Okay, and others, see, 1.5 bar is not a correct answer. 1.5 bar is not a correct answer. You check your answer, and after that we will discuss. And others also can reply. Someone wants to join. See, now students are joining. I don't know. Rajesh V. Yeah, Dalton's law you can use. Yeah, Dalton's law of partial pressure. That you are talking about, right? Yeah, that you can use. See, you read the question carefully. It is asking the total pressure in the vessel is. It is not asking the partial pressure. It is asking the total pressure. It has given the hydrogen, the pressure of the hydrogen, and it is asking the total pressure. See, it looks like only one person is taking interest. Others are just silent. No one is speaking. So please take your interest. If you are like, if you have some doubt, then that also you ask. Okay, I will give you the hint. Let us assume that total pressure is X. Then find X. What is X? Make some assumption. Then you go ahead, and then finally you find X. J Rishikesh, your answer is correct. J Rishikesh, your answer is correct. Rakesh Verma and Ijazul Rahman, you also participated. Rajesh V and Rakesh Verma, Ijazul Rahman. Can you tell what doubt you are having? Why you are not able to get the answer? Yeah. Okay. 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 So we know Dalton's law of partial pressure. Everyone knows Dalton's law of partial pressure. See, I will say the law is suppose that the mole there are two gases, the mixture of two gases, and the mole. Uh, okay, so the law is suppose that there is a mixture of two gases, and the partial pressure, like you calculate the mole factor of both the gases. So the partial pressure, like the total pressure of the beaker is in a beaker, we in a closed beaker we have the mixture of two gases, and the mole factor of one gas is 0.8, and the mole fraction of another gas is 0.2. Assume that then the total pressure of the beaker, total pressure of air in the beaker is P. Let us assume that it is P. Then then the partial pressure of the gas which is having the mole fraction 0.8 will be equal to the P into 0.8, and the partial pressure of gas which is having the mole fraction of 0.2 will be equal to the P into 0.2. Is this clear to you? Guys, is this clear to you? If no, you tell me, I will explain one more time. Okay, okay. So, no problem. Uh, Actually, this time I don't have my tablet, because of that I am facing problem. But you just cooperate with me. You will learn. There is no problem. Uh, how to? Uh, I'm not able to like write. There is one option like notepad where we can write online something, like we can sketch and we can write something. Okay, leave it. See, you mean here? Are you able to see? Are you able to see? Okay, fine. See, consider that there is a box. See, this is just a problem for this week. Next week, this won't be a problem. So just cooperate with me, and I am really sorry that I was not able to manage that tablet. Okay, so consider this is a box. Are you able to see? This is a box. It has a mixture of two gases, A and B. So the total pressure inside the box is P. So the mole fraction of A, let us consider the mole fraction of A is equal to the X. What will be the mole fraction of B? Do you have any doubt? 1 minus X? Do you have any doubt in this? No. Okay. Mole fraction of A is X. This box is having only two gases, A and B. If the yeah, if the mole fraction of A is X, what will be the mole fraction of B? What is mole fraction? Mole fraction is equal to the number of mole of A upon number of mole of total number of mole of air inside the box. Number of mole of A plus number of mole of B. Is this not the mole fraction of? Is this not the mole fraction of A? Do you have doubt? Okay. So B is equal to, this is what I can say, mole fraction of B. Mole fraction of gases of B. Mole fraction of gas B, right? So what is the Dalton's law of partial pressure? Like P is equal to the X mole fraction of A. This is mole fraction of A into total pressure plus mole fraction of B into total pressure. Wait, let's see. No. Wait. Basically, partial pressure of A is equal to the mole fraction of A into total pressure, and partial pressure of B is equal to the mole fraction of B into total pressure. And total pressure is equal to partial pressure of A plus partial pressure of B. Looks like I think I have. Okay, I will share the full solution. I will share the full solution with you. So, so is this clear to you? Is this not clear? Yes. Up to that, it is okay. Now the question is asking the total pressure P. It has given the partial pressure, right? Yeah. See, now this is 0.7 is equal to the mole fraction of hydrogen. What is mole fraction of? The partial pressure of hydrogen is 0.7 bar, and mole fraction of argon and nitrogen 0.2 and 0.6. 0.2 and 0.6. So there are three gases. Argon, there are three gases: argon, nitrogen, and hydrogen. So now you tell me what is the mole fraction of hydrogen? 1 minus 0.2 minus 0.6. Yeah, 0.2. Because total mole, the sum of all the mole fraction of sum of the mole fraction of all the gases is 1. So 1 minus 0.2 minus 0.6 is equal to 0.2. So that is the mole fraction of hydrogen. Is this clear? Now, the now you assume that total pressure is P. P into 0.2 is equal to the 0.7. Say yes or no if you are not agree. P total pressure is P and the mole fraction of hydrogen is 0.2, then P into 0.2 is equal to 0.7. That is the Dalton's law of partial pressure. What I have written here is this visible to you. Partial pressure of A is equal to the mole fraction of A into total pressure. So in this case, we don't know total pressure. So you assume that total pressure is P. We know partial pressure of we know partial pressure. So we can say like partial pressure of hydrogen is equal to the uh, mole fraction of hydrogen into total pressure. Same thing I am writing here. So, now that we need to calculate this, we know this, we know this. Yes, Basically 1 minus zero point 0.2 minus 0. See the partial pressure of hydrogen, how you will calculate? See the partial, how will you, they have given already, they have given the partial pressure of 0.7. You need not to calculate the partial pressure of hydrogen. Yes, we need to calculate the total pressure. So now you use this equation. The partial pressure of H2, what is partial pressure of hydrogen? 0.7, right? Yes, 0.7 is equal to the mole fraction. We know mole fraction. What is the mole fraction of hydrogen? Guys, take 1 minute. I will write it somewhere only then. Guys, give me a minute. I'm trying to send you the solution. Just give me a minute. Guys, are you able to see the screen? This is the question number 2. Are you able to see? Now they have given the partial pressure of hydrogen. This is 0.7. They have given the partial pressure of, sorry, they have given the mole fraction of argon and mole fraction of nitrogen. This is 0.2 and 0.6. So there are three gases in the closed chamber. So what is the mole fraction of hydrogen? 0.2, right? Now the mole fraction of hydrogen is 0.2. Let us assume that total pressure is P. This is the Dalton's law of partial pressure. P into 0.2 is equal to 0.7. So we got P is equal to 3.5. What is the doubt here? If you anyone who is having some doubt, please let me know. Should we move to the next question? Yeah. Yeah. See, one minus basically what I said, mole fraction. There, suppose that there are like there are three gases. Suppose that there are two gases, then the mole fraction of both the gases is equal to the one. So in this case, there are three gases. So mole fraction of all the three gases is equal to the one. If there are n number of gases, then the mole fraction of all the n number of gases is equal to the one. So, so like there are three gases: hydrogen, nitrogen, and argon. So the mole fraction of argon plus mole fraction of nitrogen plus mole fraction of hydrogen is equal to the one. So if you subtract 1 minus 0.6 minus 0.2, what you will get? 0.2. I didn't write it here because I thought it is a very I thought it is not needed, so I didn't write it. But this is like 1 minus 0.6 minus 0.2 is equal to 0.2. 1 minus 0.8 is equal to 0.2. Still confusion. If you have the confusion, you can discuss, no problem. Okay. Okay. So now we can move to the next question. Uh, this you try to solve the question number 3. हेलो, हाँ शिवम, अभी कैंपस में हो? यार थोड़ा टैबलेट देना अपना यार। अभी 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 ला सकते हो क्या? बहुत अर्जेंट है हमको। ना ना ना, छह नहीं, छह से ज्यादा होगा, वो हमें थोड़ा जरूरत है, तुम लाना यार थोड़ा। ठीक है, थोड़ा जल्दी करना यार। ओके ओके ओके। हाँ हाँ, ठीक है, आओ आओ, थोड़ा जल्दी करो यार, जितना जल्दी हो सकता है उतना करो, मैं क्लास चल रहा है और मुझे जरूरत होगी। ओके। या व्हाट इज द आंसर दैट यू गाइस आर गेटिंग? क्वेश्चन नंबर 3। आई विल शो द क्वेश्चन। क्वेश्चन नंबर 3। या no, no, it is not correct. Okay, so should I explain or you? Okay, I will explain. See, in this case, the system is moving from state 1 to 2 through a path. And see, first thing, work done and heat transfer both are path function. Both are path function and state function. See, I hope like what is state function and what is path function is clear to everyone. Say yes or no. Yes, sir. So, uh, the system is moving from state 1 to 2 through a path A. Heat transfer to the system is 100 kilojoule. Now, heat transfer to the system is always considered as positive. So, delta Q is positive. So Q is equal to the plus 100. And work done by the system is 50. So, work is done by the system is 50. If the system is then restored to state 1 through an adiabatic path B, the work interaction is. Now, we need to calculate the work interaction in the path B. So, see, in this case, when the system is moving from state 1 to 2, uh, in that case, delta U is equal to the delta U. Basically, what I'm saying, suppose that we have delta U when the system is moving from 1 to 2. Then the delta U in the case when the system moves from 2 to 1 is equal to the minus of the previous delta U. Because U2 minus U1 in initial case, delta U was U2 minus U1. When the through the path A, the delta U was U2 minus U1, and in the path B, delta U is U1 minus U2. Okay, so see this. Can you see the question number 3? Can you see the question? See, the system is moving from 1 to 2, and then it is coming back from 2 to 2 to 1. So delta Q is heat is added to the system. Delta Q is considered as positive, and this is in path A. This delta Q and delta W are given for path A. Yeah, see delta W and delta Q are given for path A. Is this visible to you? Okay. So in path B, they have given the adiabatic process. So delta Q is 0. In path B. Yeah. Anyone is having some doubt? In path B. Yeah, because yes, exactly. Path B is written from 2 to 1. In path A, it is moving from 1 to 2, but in that case, it is not adiabatic. They have given the delta Q. So they have said like heat is added to the system. That is why I have taken 100. The positive 100 I have taken. And the work is done by the system. That is why positive. If they said work is done on the system, then this will be minus 50, right? Okay. Okay. So in path B, delta Q is 0. This is the first law of thermodynamics. Basically, this is the first law of thermodynamics. Del Q is equal to the du plus del W. Basically, I have written delta, but it should be del because here it should be del because this is a path function, not the state function. So we cannot write delta here. This should be del. Del Q is equal to the du plus del W. Now, in first case, in the path A, in the path A, del Q is equal to the 100. They have given, and this is delta U plus 50. They have given del W. Now we need to calculate delta U. So in first case, we are getting delta U is equal to the 100 minus 50, that is 50. Okay. And so this, the see, in path A, delta, what is delta U in path A? Can you tell me what is delta U in path A? Is it U2 minus U1? You agree? Yeah. So U is a state function, right? Now in path B, what is delta U? U1 minus U2. So in path B, delta U is equal to the minus of delta U in path A. Yeah. So delta U in path A is minus 50. So that is U1 minus U2 in path B is minus 50. So in minus 50, U1 minus U2 is minus 50. And again, we will use the first law of thermodynamics. This is the first law of thermodynamics. And here we will write minus 50. And since in the path B, they have given del Q is equal to the 0 because it is an adiabatic process. So del W is 50. Now 0 is equal to minus 50 plus del W. Yeah. Now you tell me your doubt. If you have some doubt, please let me know. Yeah. Previous process means this A and B. You are asking the difference of work done in A and B. See, in in first you tell me work done is a path function or a state function. Is work a path function? See, one more thing I will say whenever I am asking the question to a particular person, only that person should speak, not the other, because I want to clear the doubt of that person. So, whoever I'm asking the question, only that person can reply. If I am asking the general question, then anyone can reply. But if I am asking to a particular person, then only that person reply. So I don't know who was asking this question. Whoever was asking that question, can you tell is the work done path function or state function? Yeah, so it is a path function. So basically, in the case in the path A and path B both are different. Path A is not a adiabatic path, and path B is a adiabatic path. So the work done is different in both the cases. And is the heat transfer different or same? The heat transfer is different in both the cases or it is same? No, no, we cannot say even if it is not a adiabatic, the path is different because you can see it is moving from a different path. It can be, can you see my cursor? If the path may be something like this, it can be anything. It can be, see, it may be hit like, see, in the path A and path B, both are not adiabatic. Even in that case, work done can be different. It not because of adiabatic, because path is different. So that is why in both A and B, since path is different, then heat and work both are the path functions. So both is different. If path is different, then heat and work both are different. Okay. If anyone is having doubt, then I can discuss. They can ask. Okay. Okay. Then I will move to the next question. Uh, please go to question number 4. Question number 4. हेलो। हाँ हाँ, यहाँ पे बैठे हैं, एक मिनट। एक एक मिनट, कॉल में आ रहा हूँ बस एक मिनट। Guys, please give me 5 minutes. I will be back within 2 minutes. I will be back. Just give me 2 minutes. By that time, you please solve question number 4. Yeah, your answer is correct. Others can also answer the question, but just give me a minute, and after that, I will explain. Yes, yes, yes. Shiva, Okay. Okay. So should I share that because I got only one answer by I got only one answer and others are you trying? No, no. Your answer is correct. Not correct. Yeah. It's correct. Yeah, it's correct. Rakesh Verma, it is correct. You need not to write the solution. You just just send the answer. Rakesh Verma, it is correct. Your answer is correct. And what about Ijazul Rahman? Ijazul Rahman, are you there? Are you trying to solve? Okay. Okay. E- Yeah, exactly. It will come minus 50 since it is asking heat loss because it specifically it is saying heat loss. That is why we are saying 50. Yes, exactly. Okay, okay. I will. Yes, yes. Sure. I just give me a minute here. Actually, what I'm trying to connect with a notepad so that I can solve in front of you. Okay. Okay. I will. Okay. I will share that. Okay. I will share this solution. This is the solution. See, basically, it is saying, hello, is my screen visible to you? Yeah, yeah. Okay. See, in question number 4, we will apply that steady flow energy equation. So they have said like, hello, am I audible? Yeah, yeah. So just we need to apply the steady flow energy equation. So they have they have given that delta kinetic energy, change in the kinetic energy and change in the potential energy is zero. Now you tell me, is the kinetic energy and potential energy a state function or path function? Is kinetic energy a state function or it is a path function? State function. Yeah. I hope everyone is agree. State kinetic energy and potential energy is a state function. Not only the kinetic energy. That energy is a state function. Maybe internal energy, kinetic energy, potential energy, whatever it is, but it will be a state function. So this kinetic energy is a state function. Now we will apply the steady flow energy equation. So this is the steady flow energy equation. Uh, so in state one, total energy in state one plus heat added to the system in state 1 is equal to the total energy in state 2 plus work done by the system. This is the steady flow energy equation. Is anyone is having some doubt in this equation? Yeah, it's fine. So they have said like delta kinetic energy. So I have like deleted this term and change in the potential energy I have deleted because they have given that change in the kinetic energy, potential energy is negligible. So finally we are getting this equation Q is equal to the H2 minus H1 plus W. Now they have given the H2 minus H1. They have given or like what they have given? They have given H2 minus H1 or they have given CPCV. What they have given? They have given the enthalpy. Question number, yeah, 100. Yeah, yeah. They have given the enthalpy. So just H2 minus H1. So this will come minus 150 plus W, work done. Now in this case, work is done by the system, right? That is why I am taking positive. If it were work is done on the system, then it will become negative. No, no, I didn't get you. What did you say? Yeah, enthalpy will decrease, but here, see, this steady flow energy equation is valid everywhere. So it is not only valid to turbine. So simply I am using the steady flow energy equation. That is conservation of energy in an open system. That's it. So just I bring this H1 term to the right hand side. That is why I have written H2 minus H1. Now simply H2 minus H1 is minus 150. Now they have given work is done by the system. That is why I have written positive plus 100. Minus 150 plus 100 minus 50. Now the Q is equal to minus 50. Minus 50 means work is, sorry, heat is rejected by the system. So that is why they are asking what is the amount of heat that is rejected by the system. So it is minus 50. Minus 50 since they are especially asking rejected by the system. That is why like our correct answer is 50. Suppose that if it were a compressor, then they have, see, in that case H2 will be greater than H1. Yeah, yeah, yeah. See, is this clear to everyone or anyone is having some doubt here? If anyone is having some doubt, I can explain it. Yeah, yeah, yeah. Please ask. Yeah, yeah. See, just you do a simple calculation. See, suppose that the temperature is changing by maybe 5 degrees Celsius, and by that time, speed is increasing by suppose the temperature is decreasing by 10 degrees Celsius. You, whenever you are free, you do a calculation. Then the change in the suppose that temperature consider this case only. I will do the calculation. See, this is a I am very happy that at least someone asked some question. Okay. In majority of the cases we are neglecting it. So consider this case only. uh, Here they have given the mass flow rate. Did they give the mass flow rate in that? Okay, consider air. Consider air and mass flow rate is 1 kg. Now in that case temperature is decreasing by 10 degrees Celsius. So delta H will be, what will be the delta H? M Cp into delta T. M's, yeah, yeah, because this is a flow system, so it will be delta H, not delta E. Yeah, yeah. So like now we have considered one into Cp. Cp will be for air. Cp is one, right? 1 kg per kilojoule. 1 kilojoule per kg Kelvin. Cp. So into delta T 10. Mcp delta T will come 10 kilojoule. Delta H will come 10 kilojoule, right? uh, Basically delta H will come 10 kilojoule per second if the mass flow rate is 1 kg per second. So delta H will be 10 kilojoule per second. Now in this case, suppose that velocity is increasing by 10 meter per second. Just imagine, just consider a hypothetical case and velocity is increasing by 10 meter per second. What will be the change in the kinetic energy? 1 by 2 into m into v square. No, no, mass flow rate will remain constant. Mass flow rate, how the mass flow rate will change? Mass is constant, right? No. See, even if you use rho AB, then the density will change, but mass flow rate will remain same, right? Mass flow rate, until unless you are adding the mass or you are taking the mass out, mass flow rate will not change. So mass flow rate is 1 kg, right? So initially increase in initially consider that it was maybe zero. Consider that initially it was 1 meter per second. After that, it will become 11 meter per second. So if you do this calculation, the 11 square minus 1 square, what will be 120, right? 120 upon 2, it will be 60. So 60 joule per second, right? Now, what is the delta H? It was 10 kilojoule per second. Delta H is significantly higher than the delta kinetic energy. Are you agree or not? Yeah, you are agree or not? Yeah. Yeah. So that is why we are there. Because delta kinetic energy is significantly less than delta H. That is why majority of the cases we are neglecting the change in the kinetic energy. Yeah. Because it is very less. If you compare the change in the kinetic energy as compared to the change in the enthalpy, then it is very less. In any case, you can do this calculation, and in majority of the cases, if you see do the similar calculation for change in the potential energy, in that case also you will get the same result. Like change in the potential energy significantly less than the change in the that change in the enthalpy. That is why we are neglecting it. Okay. Yeah. Uh, Ijazul, 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 is this clear to you? Is the question number 4 clear to you? Okay. Okay. Now we will move on to question number 5. And now question number 5, you try to solve question number 5. Basically here the value of CB and CP. CB is 0.7 and CP is 1. This is CB and this is CP. There is some printing mistake. It should be CB and it should be CP. CB is equal to 0.7 and CP is equal to the 1. Huh? Is, no, I like is this so okay, is this so question is not visible? No. Is like no one is able to see the question. It's like or what? Yeah, now I have changed. Now it is the question dash only. It is visible. So I cannot do more than this. Question number 5. You need to use the simple steady flow equation. That's it. Yeah. Yes, yes. CB is 0.7 and CP is 1. Yeah. 0 kilojoule per kg Kelvin. Yeah, you are close. Your approach is correct, but you have done a silly mistake. Yeah. Yeah, yeah. I will say you read the question one more time and think that this is not a flow system. Here it is not a flow system. Think in that way. Here that fluid is not flowing. It is they have never like nowhere they have mentioned that fluid is flowing. It is like a fluid in a cylinder piston a type of arrangement where it is not flowing. Okay. So today, yeah, that is correct. Yeah, in this case, you are actively participating. I am very happy that like others also try to solve. Okay. Okay. Now I will say, see, uh, like Ijazul and Rakesh and Rajesh already gave the answer, and Rishikesh. I hope you tried with using that steady flow energy equation. Did you try using steady flow energy equation? I will share the question. Okay, okay. Now I will solve it. Anyone else can give the answer. If it is wrong, that is also fine, but at least you say something. If not, like you tell me what is the doubt. That is also you tell me. Yeah. Okay. 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 Okay, so in this case, see, it is like in this case, since there is a no flow, see, there is a difference between the question number 4 and question number 5. In question number 4, the air is flowing through the turbine, like air is in and then air out. So there is a flow. When there is a flow and you are using the steady flow energy equation, then you will use the enthalpy term. This enthalpy term you will use. But if there is no flow, suppose that it is some kind of cylinder piston arrangement where uh, yeah, okay, suppose that some arrangement is there like this, and in this arrangement this piston is moving up, but there is no flow. So now in this case you want to use the steady flow energy equation. So in this case you won't use H, you will be using internal energy, you will not be using enthalpy, you will be using internal energy. So everything will remain the same. Just in place of H1, you will be using U1, and here you will be using U2. So now in this case, you neglect the change in the kinetic energy, change in the potential energy. So the equation will become now this equation will become uh, question number 5. So this equation will become U1. See, in this case, suppose that you are using in place of H you write U1 and U2. So change the negative, and so it will become U1 plus Q is equal to the U2 plus W. So this is the equation U1 plus Q is equal to the U2 plus W. Now mCp into T1 U1. See, it is like it is given that for like there is an assumption of ideal gas. So U1 we can consider mCp into T1, and U2 we can consider, sorry, here it should not be mCp, here it should be mCb. It should not be mCp, this is wrong. Here mCb, U1 is mCb into T1 and U2 is mCb into T2. So here it will come, this is a mistake. So it should be Cb, it should not be Cp. So here W is equal to the mCb into T1 minus T2 plus, sorry, didn't get you. What? No, 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 no. It is not constant volume. See, the thing is, either it is a constant volume, constant pressure, whatever be the process. If it is saying delta U, then delta U is equal to the Cv into delta T. It doesn't matter the type of process it is. You agree or not? If not, you tell me. No, 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 no. We cannot replace Cp. Why? Because there is no flow. See, there is a difference in this case and in this case. In this case, there is a flow that air is coming in and air is going out. See, consider a compressor. Air is coming in, air is going out. But consider this cylinder where air is not going out and going in. It is that air only, and that air at constant pressure it is expanding at constant pressure. Yeah, yeah, yeah. It is a closed. Yeah, it is closed system, not kind of. It is a closed system. Oh, so that is why we are using in the closed system. If you use that steady flow energy equation in closed system, everything will remain same. Only this term will become U1 and this term will become U2. And you this equation you will become you will get U1 plus Q is equal to U2 plus W. So U1, since they have given that it is an ideal gas, so U1 is equal to mCV into T1 plus Q is equal to the mCV into T2 plus W. So W is mCV into T1 minus T2 plus W. What I guess W is equal to the plus 20. So if you solve this equation, you will get 6. That is the correct answer. Is this clear to everyone? If anyone is having some doubt, please let me know. Yeah, 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 yeah. See, just give me. Suppose that there is a pipe. Maybe you consider this is a pipe, and some air is coming in and air is going out. Air or any fluid is coming in, or any fluid is going out. See, you think in this way: if the air is flowing, if it is flowing, it has some velocity. Then in that case, you use H, enthalpy. No, steady or unsteady means, steady means, if suppose that this is your control volume and with the time it is changing, then that is unsteady. If with the time it is not changing, then it is steady. Suppose that here the flow rate is maybe 2 kg per second. Here the flow rate is also 2 kg per second. So there is nothing is changing with time. And the mass is coming in, same amount of mass is going out. If temperature and everything is same, it is not changing with time, then that is steady. If it is changing with time, the inner condition is changing with time, then that is unsteady. So it is not related to steady and unsteady. See, try to think in this way. In this case, there is a flow. This whatever, suppose that there is an air in this region, and you are applying the energy equation in the air in this region. So that air is flowing. Similarly, this air, you are applying the energy equation in this region, and the air is flowing. So that is why we are using enthalpy term, not internal energy term. Now, in this case, suppose that in one case there is air in this region, there is no flow in this case. Now again it will move to another position, and this will become, and again you are using, suppose that, and it constant pressure it expands and it reaches this state. Now in this case again there is no flow. It has moved from this state to this state. Now nothing is changing. Air is not flowing. So we will use internal energy, not enthalpy. In this case, we will use internal energy. And since we are using internal energy, so we are getting delta U term. Yes, internal energy of the gas particles under the volume. Uh, and anyone else is having some doubt, please let me know. Okay, should we move to the next question? One student has left. Okay. Please go to question number 5. No, no, question number 5 we have already solved. Please solve the question number 6. This question everyone should answer. Yeah. Question number 6. Yeah, answer is correct. Question number 6. Everyone should answer. I want everyone to answer this question. If you are not answering, then you let me know what is the conclusion. That J Rishikesh 5.2. Your answer is correct. Rajesh Verma and Rajesh V and Rajesh Verma are both are same or different? Rajesh V and Rajesh Verma. No, no, no. It's okay. Rajesh V and Rakesh Verma. Ijazul Rahman. Okay, you are getting the different answer. Okay, no problem. Ijazul Rahman, what you are getting? 6.2. Okay. Okay, okay. Now I will explain it. See, correct answer is 5.2. So now you see the solution. Basically, what is COP? COP of the refrigerator. Yeah, coefficient of performance. The yeah, uh, that refrigeration effect to the one done by the compressor. Yeah, exactly. Okay, see the solution. I will share the solution. See, this is this we studied in class 11. We remember that this diagram was there. Okay, in the NCERT book, this diagram was there. So this is like, suppose that this is a system. This is your refrigerator. Basically, this is a system, and it is taking the heat from the refrigerator, and that is at temperature T1. So T1 is less than T2. It is taking the heat from T1 and it is rejecting the heat at T2. So it is taking the heat Q1 and it is rejecting the heat Q2. So W is equal to the Q2 minus Q1. Just use the conservation of energy. That's it. So W is equal to the Q2 minus Q1. So Q1 upon Q2 minus Q1. So here bring that Q1 term in denominator. So it will become 1 upon Q2 upon Q1 minus 1. If you have any doubt, please let me know. So they are saying it is an ideal gas. So this will here you that C this Q2 is equal to Cp into T2, Q1 is equal to the Cp into T1. So 310 upon 260 minus 1. 1 upon 310 upon 260 minus 1. Now if you do this calculation, you will get 5.2. You agree or not? If anyone is having some doubt, please let me know. Yeah. Ijazul, Ijazul, are you getting 5.2? Yeah. Okay, so we will go to the next question, and the next question is question number 7. Try to solve the question number 7. Just use the steady flow energy equation and think that there is a flow or there is no flow. Just think in that way. Use the steady flow energy equation, you will get the answer. There is an assumption of adiabatic duct means delta Q is equal to 0. Since this is a duct, it's like throttle valve, so there is no work done. And neglect the change in kinetic and potential energy. And what will be the temperature T2? See, think in that way. In this case, uh, I will give you a hint. See, the throttle valve is just a very thin pipe. Now, this thin pipe, here the air is coming in, here air is coming out. It is adiabatic, so del Q is equal to the 0. There is no work output, so del W is equal to the 0. Now use the energy equation, use the steady flow energy equation. H1, consider this is 1, this is 2, H1 plus 1 by 2 into M into V1 square plus M G into H1. This is height, this is plus heat added to the system is equal to the H2 plus 1 by 2 into M V2 square plus mg into H2 plus work done by the system. Yeah. Now you neglect it. See, they have given it adiabatic, so there is no heat transfer, so you neglect Q. Neglect the change in kinetic and potential energy. Now you are getting H1 is equal to the H2 plus W. So there is no work done, so you can neglect W also. Here you are getting H1 is equal to the H2. Now for ideal gas, uh, enthalpy is the function of temperature. What should be the T2? Not a single answer, but at least one person should give the answer. Yeah, that is the correct answer. Simple. Both the temperatures are same. Yeah. What temperatures are? Yeah, yeah. Enthalpy is a function of temperature, and here it is H1 is equal to the H2. Is this clear to everyone? I hope it is clear to everyone. Ijazul Rahman, can you speak? Are you there? Ijazul, are you there? Yeah, yeah. So is this clear to you that T1 is equal to the T2? Okay, okay. So other than for others, it is clear, right? Okay, okay. Yeah, yeah. Okay, I will explain it. So you see this calculation. You see this calculation. See, in this case, it is moving from state 1 to state 2, and it is adiabatic because of that del Q is equal to the 0. And from 10 bar 300 degrees Celsius to 0.1 bar, if you use this equation, same equation, see here, you neglect the change in kinetic energy, neglect the change in potential energy, equation will become H1 plus Q is equal to the H2 plus W. In this case, Q and W is also 0. So H1 is equal to the H2. So this is the equation that we will get. This is the equation that we will get. H1 plus Q is equal to the H2 plus W. In this case, Q and W both are 0. So H1 is equal to the H2. So that is giving the T1 is equal to the T2, because here they have given that temperature enthalpy, it is they have given that it is an ideal gas. For ideal gas, enthalpy is only the function of temperature. Okay. Okay. So there are few more questions, and so we will stop now. And in the next class, we will solve other question. And after that, I will give this question to you, and I will give the solution as well. So you can, if you have some doubt, you can discuss with me, or I will give you my email ID. You can ask your doubt through the mail ID also. That is also not a problem. Okay. Okay, guys. So we can stop now, and next class we will having on the next Friday. We will having the next class. So every one of you please join, right? Will you? Everyone will join, right? Okay. Okay. One more thing. Yeah. 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 See. See. No one should leave. See. Just listen to. I want to say something. Yeah. So do you think like I can improve the class somehow? So you tell me so that I can improve the class. If you want to add something, or do you want to improve the class somehow, so I will add this, I will add that part. You just, yeah, yeah, yeah. See, the next time I will write, I will solve the question in front of you, like someone is solving in the blackboard. I will solve like that. Anything else? Like one student said, like I need to add some part of psychometry, I will add that. And if you have some question, you bring that question. Next time you bring that question, we will discuss that question also. Okay. Yeah. In question number 5, question. Yes. Yeah. 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 See, that is on. Yeah. You tell. Uh, it is positive 50. It is positive 50 because, see, the correct answer is positive 50, because the question is asking that heat loss. That is why we can say positive 50. Here, there, like I should add one more step here, that heat loss is equal to 50. Q is equal to minus 50. Heat loss is equal to 50. In fact, 50 kilojoule. Yeah. That is correct. Okay. Oh, Ijazul, any suggestion from your end? Okay. So I will share that question in next class. I will share those questions and answers, everything with you, and we will discuss. And you bring your questions also. We will discuss those questions as well. Okay. Thank you. Guys, you can leave now.